Hello, my name is Rob Reynolds. Welcome to Mat-073. Today we're going to get the last section in Chapter 6, 6.8, and it deals with the topic of complex numbers, which is introducing the idea of an imaginary number which have real-world applications. And an imaginary number, we let it be the letter I, and the letter I happens every time you take the square root of a -1. So if you had like the square root of -4, we used to call that undefined. Well, today we're going to define this as the square root of 4 times the square root of -1, which is a 2 and I. So we can add and subtract these complex numbers in the form of a plus bi, where a is a real number and this bi is the imaginary part. We can multiply them, we can divide them. So we're going to be looking at, again, complex numbers and the number system. So before this lesson, we could not take the square root of negative numbers. After this lesson, we're defining that the square root of -1 is an imaginary number. So here comes, again, definitions. If you have the square root of a negative number, you can actually rewrite this because of the property the square root of ab is the square root of a times the square root of b. And the square root of this -1 is going to be the imaginary number. So I'll rewrite this as the square root of -1 times the square root of 9. The square root of -1 is I, and then 3, but instead of I3, we usually write this as 3i. It's kind of like x5 is the same thing as 5x, but x5 should look funny to you. So I times 3 should look funny to you. We'll have 3i, just like we write 5x, I'll write 3i. We can also take the opposite of this. So every time you take the square root of a negative, I teach that an I pops out. So this is actually an I, square roots of 48. And I think I can simplify the square root of 48. All I have to do is find a perfect square. Perfect squares are like 4 and 16, 25. I need to find one of these numbers that goes into 48. And I think 16 does, 16 times 3. So I'll write this as -I times 4 square roots of 3. And my final answer will be -4i square roots of 3. And here's how the author worked it out. So again, imaginary numbers is the second part of that complex number. So in the form of a plus bi, which is all complex numbers, because I can write 5 as 5 plus 0i. So and this is a real number, this is a complex number, and I can write an imaginary number as 0 plus 3i. This is an imaginary number, and this is the complex number. Anything written in a plus bi form is complex. And here's kind of a chart of the breakdown where sometimes where b is 0 and b is not 0, again in that form a plus bi. If b is 0, that's going to drop that out, and then we just get rational numbers and irrational numbers. But a complex number or an imaginary number has just the I in it, but then the complex number is always in that form, a plus bi. So what can we do with these? Well, we can subtract, we can add, we're going to learn how to multiply and even divide imaginary numbers. And they work pretty much the same as a variable like x. And the other thing that we need to kind of discuss a little bit is if we define I as the square root of -1, then if you square both sides, we'll end up with I squared is equal to -1, which is a very powerful definition because actually we're changing an imaginary number into a real number by squaring it. So let's take a look. First of all, we're just going to look at how to add these, and adding them, we're really just going to combine the real numbers with the real numbers and the imaginary numbers with the imaginary numbers. So you can think about adding like terms. This 3 is just like this 7, so we'll just add that straight down for 10. And then I'll combine my imaginary numbers too. It's kind of like 2i and 8i for 10i. And we can subtract, you distribute this, so this, and after you distribute, the parentheses go away, so minus 9 minus 1, make sure you get that changed. And then I just combine. 10 and negative 9 is 1, and then combining the negative 2i and the negative I, signs are alike, we add, keep the common sign. So final answer is 1 minus 3i. We can also multiply square roots together, but be careful, we don't want to call this the square root of negative 6 times negative 5. I'll say does not equal, because that would be a positive square root of 30, and look, the answer is actually negative square root of 30. So order of operations says you've got to take care of the imaginaries. Remember, the rule is every time you see the square root of a negative, an I pops out. So we need to do order of operations. We need to take care of that procedure first. So that's what they're saying here. This is not the square root of 15. This is really I square roots of 3 times I square roots of 5. And remember, that's the same thing as I squared times 3 times 5. And then because of that I chart, if I is the square root of negative 1, I squared is negative 1. And again, the reason why is because if you square this, I'll get just negative 1. So this is a negative number, negative 1 times the square root of 15, which is really negative square roots of 15. So be careful with order of operations here. Same thing. This is I square roots of 2 times I square roots of 10. That's I squared square roots of 20. Oh, I think I can break down 20 as well. We now have a nice definition that I squared is negative 1. And 20 is really 4 times 5. So I'm going to bring this 2 out front. This is really negative, well, negative 2 times negative 1 is negative 2 square roots of 5. Author agrees. Let's distribute. This is going to be 10i plus 6i squared, but remember, I squared is really negative 1, so the final answer is 10i minus 6. Or put it in the form a plus bi, probably even better. Let's FOIL this out. First, outer, inner, last. My first terms is 8. Outer terms is negative 6i. Inner terms is 4i. And the last term is a negative 3i squared. Remember, I squared is negative 1, so that's really a positive 3 plus that 8 is 11. And then I can combine these green terms. So negative 6 plus 4 is negative 2i. 11 minus 2i. Author agrees. So we can complicate things a little bit more by talking about what I cubed is equal to. Well, I cubed is really I squared times I, because you rewrite the base and add the exponents, but this is I squared times I to the first, because you rewrite the base. 2 plus 1 is that 3. But I squared is negative 1, and negative 1 times I is just negative I, which is what they have here. And we can do something similar with I to the 4th, because I to the 4th is really I squared times I squared, which is defined as negative 1 times negative 1, and we get a 1. And then notice that this chart repeats. Every multiple of 4 equals 1 again, because we can rewrite I to the 8th to be I to the 4th squared. And we've just defined I to the 4th to be a positive 1. So this is 1 squared, which is back to 1. So I to the 23rd can really be written as I to the 20th times I cubed. So I to the 20th is a power of 4, because we can write it as 4 to the 5th. So that's just really 1 to the 5th, or just 1, because every multiple of 4 equals 1. And then I cubed, well, I could use the I chart for I cubed and get negative I. Or you could do this process again and get negative I. So basically there's 4 i's that we need to worry about. So this is I cubed turns out to be a negative I. So that the final answer is just negative I, which is what they did. So I to the 40th, it's a multiple of 4. I know the answer is 1. The closest multiple of 4 to 33 is I to the 32. 32 divides by 4. And then that leaves me with one I left. So this is 1 times I, or the answer is just I. There it is. There's that I to the 32 times I. They wrote it out just a little bit differently, but the concept's the same. I'm just looking for a multiple of 4. And 32, 16 times 2, power raised to a power, is a multiple of 4, so that's just a 1 times I, and the answer is just I. So again, conjugate means change that middle term. So if you have an a plus bi, we're going to rewrite that as a minus bi. So the conjugate here, they just asked for the conjugate, change the middle sign. If you have a negative out front, we don't change that. Its conjugate says change the middle sign. And if we don't have anything, you could think about this as 0 plus I. So the conjugate of that would be 0 minus I. Or you would probably just write negative I. Good. Author agrees. Negative I. So why is the conjugate so important? Because when you start dividing, it comes in really handy, because when you try to rationalize the denominator, which means get rid of, remember, if you have a 1 divided by I down there, that's the same thing as 1 over the square root of negative 1, and that's not rational. You've got to get rid of that radical in the denominator. So a strategy is, if you see 1 minus I, the goal is to multiply the numerator and the denominator by its conjugate, 1 plus I, and then notice that will rationalize the denominator. Because an imaginary times an imaginary is real, negative 1. So let's start with multiplying. Notice these are conjugates. This is the minus, this is the plus. So what's so powerful about a conjugate? Well, when you FOIL, your outer and your inner terms should disappear. And the reason why is because the outer term is 14i, and the inner terms is negative 14i, and that'll cancel. So the only thing I really have to worry about, if it really is the conjugate, is the first terms and the last terms. So the first terms is easy. 7 times 7, 49. The last term is a little bit harder because it's negative times positive. 2 times 2 is 4, but then I have a I times I, or I squared. Well, that's really 49 minus 4 times negative 1, which is really 49 plus 4, which of course equals 53. Author agrees. So here we go. We're dividing. So to simplify this, we're just going to multiply both sides, or the numerator and denominator, by the square root of I. You would have done the same thing if you had like 5 over the square root of 3. If you remember, to rationalize this, you would multiply top and bottom by the square root of 3 to end up with 5 square roots of 3 over 3. It's the same principle. I'm just multiplying top and bottom by I this time. So distributing, I get 3i plus 2i squared all over I squared. But remember, I squared is always defined as negative 1. So this really becomes 3i minus 2 over negative 1, which normally we probably would throw this negative 1 out front and make it the opposite of 3i minus 2, which, if you distribute, becomes negative 3i plus 2. And if you write it in a plus bi form, we'll say maybe 2 minus 3i. Author agrees. Conjugate, again, says change that middle sign. So to rationalize this, you can explore, but multiplying top and bottom by 3i will not work. You have to do 2 plus 3i in order to get the denominator to be rational. So now all I have to worry about, since I have the conjugate, is first terms in the denominator and the last terms. So let's go for the denominator first to make sure it's rational. I get 4 minus 9i squared. And of course you recognize that as 4 plus 9, I hope, which is a 13, which is rational. In the numerator, we're going to have to FOIL this up. First terms is 8. Outer terms is 12i. The inner terms is 2i for a total of 14i. And then the last terms is I times 3i, so it's positive times positive, which is a positive. but it's positive 3i squared, which will turn out to be 3 times negative 1, or negative 3, which gets combined with the 8. So 8 take away 3 is 5 plus 14i, all divided by 13. They broke it up into be that, so they took this answer, 5 plus 14i divided by 13, and they wrote it in this a plus bi form. I'm not sure if that's really necessary, but if the directions say write a complex number, then that's what they're looking for, a plus bi. So to determine whether something is a solution or not, all we have to do is plug this in and evaluate. So let's try it. 1 plus 3i quantity squared plus 5 times 1 plus 3i minus 12. Let's check to see if it equals 0. So over here I'm going to use my definition, squaring the first, twice the product, and square the last. Well, that's a 9i squared, but you should know that now as negative 9 with the 1 is negative 8 plus 2i. If I distribute this 5, I'll get plus 5 and 15i, all minus 12. And again, I'm checking. I wonder if that's equal to 0. So let's combine some terms. Oh my gosh, I don't think I'm going to get 0, because I don't see the I terms dropping out. And I'm not sure how far you need to go. I'm pretty convinced that this is not going to equal 0, because I'm going to end up with some i's. I mean, if this would have been 2i and this would have been a negative 2i, then I'd be getting closer. But I'm pretty convinced this is not true. If you want to go all the way down and just find out what that's equal to, you can. Evidently it's negative 25 minus 9i, but I think for the sake of this, it says determine whether it's a solution. I think I can tell pretty quickly that's not going to be equal to 0. Alright, I hope you found this video helpful. Complex conjugate numbers are probably new to most of you. If you have any questions, feel free to email me.